Now, one question that came quite frequent in your pre-reports is about the electric field in metals. So why don't we have electric fields inside metals? That was one of the common questions. Okay, any answers? Why don't we have electric field inside the metals? So, inside conductors, why don't we have electric field? Why can't we create some electric field inside a conductor? Okay, that's an explanation. So, in objection to that, why can't we create electric field inside a conductor? So let me write it down. There are. By the way, this is not what I said. This is wrong. We can have electric fields inside conductors. We cannot have electric fields inside conductors in electrostatics. But there's a huge difference between these two statements. This talks in general. Can we have electric field inside a conductor? We can create electric fields inside conductor. I mean, now, whenever we turn on the light switch, we are creating electric fields inside conductors. Whenever you connect a battery, we are creating an electric field inside the conductor. But it's not an electrostatic case. It's a case in which the charges are moving. That is what distinguishes a conductor from other materials, because if there is an electric field inside the conductor, then the charges start to move. It is no longer electrostatics. Only in electrostatics we cannot have electric fields inside, because what happens is, let's say we had already studied these parallel plates. Let's say that we put some positive charge here, some negative charge over there. Now this creates some electric field. And whatever material you put in between these plates, there will be electric field inside that material at that instant. So let's say if you put some material inside, let's say it's a conductor. Now, not any conductor, but let's say a metal. The difference between a metal and metal is a conductor, but not all conductors are metals. Now, in a conductor, for example, if you dissolve salt in water, the water becomes a good conductor. Not because the electrons are free to move. We have positive and negatively charged ions, both of which are free to move. So whenever you put connect a battery, these ions start to move. Now, in metals, we have the electrons that are free to move. So you put there is the parallel plates, you put some metal inside. The positive charges are fixed, they are not free to move. The negative charges, the electrons will be able to move inside this metal, and where will they go? The electrons? To the left, to the right? It's to the left, toward the positive charges. So we have we will have an accumulation of negative charges over there. So we have a current now. At the moment that we put some metal inside an electric field, we create a current. So it's no longer, it's not an electrostatic system. So we have the negative charges over there. This part is left positively charged. So it is just as if we have a negatively charged, a second negatively charged plate over here, a second positively charged plate over there, this will create an additional electric field in the opposite direction to the original one. So this will be the new electric field. So if you just pick up any electron inside this metal, it will feel both of these electric fields. The electric field created by these external charges and also the electric field created by the charges inside the metal. And if it feels some net force, it will keep moving. If you have an electron, if this electric field is weaker than the external one, the electron over there will keep moving towards the positive charge, increasing the strength of this newly created orange electric field. And this process will continue until the newly created electric field is equal to minus the external one. Now the total electric field will be this newly created one plus the external one, which will be equal to 0. Now, until this condition is satisfied, there will be a current in my system, in the metal. And once this condition is satisfied, the current will stop. But once this condition is satisfied, the total electric field inside the metal will be 0. So that is why, if there are no currents, that means this condition is now satisfied. There is no electric field inside my metal. It is only true in electrostatics, when the electrostatics is reached. So you see, we have a conductor. We put a positive charge over here. Well, it will be more or less the same. We will have negative charges accumulating here. Positive charges will be on the other side. The external electric field is in this direction. Now this is the external. In the absence of this conductor, this is the electric field of the positive charge. Let's call it E1. E1, electric field of point charge in the absence of the conductor. So we have this point charge. It creates an electric field which is radially outward. Then we put a metal in it. Now again, the electrons, they will feel some force. They will feel a net force and they will start flowing. So you see, there are more. The electric field is stronger here, so you will have more electrons in this region, less electrons on these points which are further away from my point charge. And then I will have some positive charges accumulating on the other end. And of course, there will be probably some positive charges also here. It will not be uniform. Since the external field is not uniform, the charge distribution also will not be uniform. So now there is an additional electric field created, and this additional electric field created will have this tendency. And this additional electric field, there will be a current flowing inside the conductor until this additional electric field balances the external electric field that we applied. And once they are equal, the current will stop. We have the electrostatics, but once they are equal, there is no electric field inside the metal. Just ask in a moment. Okay. I couldn't follow your question. Okay. 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 The external charge, you mean? Okay. No, I mean, here we are not considering the cases in which you can take electrons out of the conductors. Okay. Okay. Oh, just these systems and nothing else. I mean, in that case, you don't really call it a conductor. You have a proton-electron system. You don't call it a conductor. You have point charges that are free to move. I mean, usually when we talk about conductors, we think about these macroscopic objects where the charges you can treat as if they are continuous, not point charges. Now, back to his question. Mm-hmm. Well, there are interactions here, yes. Any answers? The electric field lines should not cross. But here they are crossing, no? The total electric field lines cannot cross each other. I mean, here I'm just dividing the electric field into various components. So I have the E total is equal to E1 plus E. Now the electric field lines corresponding to this E, they cannot cross each other. Neither the electric field lines corresponding to E1 nor the electric field lines corresponding to E total. But the electric field lines corresponding to, I don't know, E1 and this E, well, they are completely independent, unrelated electric field lines. They can cross. A very short amount of time. Sure. I mean, in a real world example where you have very few atoms, you have a finite number of electrons, finite number of positive charges. In this case, the maximum electric field inside that you can create is when one of the charges is moves all the way to one side, the other side moves all the way to the other side. This is the maximum you have. If you exert a larger electric field, then you are breaking up your system. Your system will break away. It will not be a static system, that's for sure. But in all of the examples we will deal with, unless you are explicitly given the number of point charges, we will always assume that the negative charge, there are infinitely many negative charges, infinitely many positive charges, and the next thing has some given charge. That will be the system that we will be interested in. Of course, if you have to take into account a finite number of negative charges and finite number of positive charges, there will be additional complications, but we are ignoring those cases. Okay. No, these are E1. They are not E total. This E is not zero outside the conductor. We also have some electric fields outside. Yeah. So these will be the ones that modify the electric field outside, so that when the electric field lines enter into the conductor, they will be perpendicular. Other questions? Now let's do a few more applications of Gauss's law. Now let us consider a sphere. I mean, on Thursday we calculated the electric field of a point charge. We calculated the electric field of an infinite line. And today as an application, we will use the electric field line of a sphere and electric E of an infinite plane. And let's also do the charge density on the surface of a conductor. Now let's start with a sphere, a finite sphere, not a point charge. This is our sphere. Let's say of radius r, and it has a total charge q. Now what is the electric field? The charge q is uniformly distributed over the volume of the sphere. Both inside and outside. Now outside no, but inside, and also very small on the surface. Now you can say, let's call rho q over 4 over 3 pi r cubed. This is constant. No, this is a constant. No. This is the charge density. So if you take some volume, the charge of that volume will be rho times delta V. If you take a very small volume, delta V, then the charge of that volume will be just rho times delta V. This is what we mean by uniformly distributed over the volume. Now, how can we find the electric field using Gauss law? Why sphere? Because of the? Why? Why? With a cube. Gauss surface. Okay. So your friend is proposing to choose such a Gauss surface. Okay, it's a cube, but two-dimensional cube. Why sphere? Why? What is the direction of the electric field? In order to apply the Gauss law, you first have to choose a Gauss surface. In order to choose a Gauss surface, you have to have some motivation to choose a sphere, a cylinder, a cube, or whatever you want. What is your motivation to choose a sphere or a cube? I mean, to determine the Gauss surface, you first have to analyze the electric field. How does it look like? What does it depend on? Which parameters it should be independent of? Yes, it's a filled sphere. The charge is uniformly distributed over the volume. Now, what shape should we choose? What is the direction of the electric field? Let's say it's positively charged. Can we have, for example, electric fields, well, this is a sphere, not a circle, of this form? Is it possible to have such electric fields? Why not? All of them are pointing outward. Oh, okay, sorry. Okay. So now it is possible, right? They are perpendicular to the surface. What is wrong with such an electric field? Why? Now this is the only charge distribution we have. Why? Okay, they will be radially outward. That is the answer. This is definitely wrong. But why? Okay, you failed to convince anybody. So let's see. I mean, if you, your answer should also explain why the electric field lines of this configuration shouldn't be radially outward. I mean, of course, this will be radially outward. Everybody is asking you questions in which the electric field is either radially outward or just straight. I mean, those are the simple questions that we can solve. But the real explanation should also make the distinction between these two. Your answer should explain why the electric field in this case should be radially outward, and at the same time why the electric field of this configuration shouldn't be radially outward. Yes, the magic word. Which one? Yes. Yeah, which symmetry? Well, okay, that's the magic word, but it's like, yeah, anyway. So what does it mean? Well, that's a nice explanation, but it fails one point. The electric field of this charge distribution from very, very far away will also be radially outward. Your first part of the explanation, at least, cannot distinguish these two. Very, very far away, both of these charge distributions, they just look like point charges. So the electric field will be radially outward. But you have the key point. It is related with symmetries of the system. What do you mean by symmetries? Symmetries are things, operations that you do on your system which do not change your system. Okay. Okay, this is the line that connects our point to the center of the sphere. For example, you can just take these two small volumes. This will create an electric field in this direction. This will create an electric field in the other direction. The combined system will have an electric field in this direction. Now that's what we basically mean by symmetry. There is this point, there is a symmetrically opposite point. These two, the electric fields of these 2 points will have an electric field in the radially outward direction. And since we are talking about the sphere over here, for every small element that you take on one side, there is a corresponding symmetric element on the other side. So it always exists, so you have this radially outward electric field. You cannot guarantee such a symmetric, an alternative, the existence of this point in this case, because it's not a symmetric shape, so not every point has a symmetric counterpart. Well, that is one possible explanation. Now, another thing that you can use is just imagine a mirror. If you just put a mirror over here, or anywhere, in fact, if you just put some mirror over there, the charge distribution doesn't change. So the electric fields should not change if you put a mirror. But if the electric fields are bending like this, they will look different in the mirror, although the electric charge is the same. So this is what we call the mirror symmetry or the parity symmetry. Now another symmetry that we have is rotations. Under rotations, the charge distribution doesn't change, so the electric field should not change. But this configuration does have that symmetry. If you rotate the electric field, it doesn't change. These lines are also symmetric, but nevertheless, they don't satisfy the mirror symmetry, and hence, the only possible configuration we have that does satisfy this mirror symmetry will be the radially outward. And it's basically, I mean, it's saying the same thing in a different world, in a different words. I mean, you see this point and this symmetric point are nothing but mirror symmetric points relative to this mirror. So the existence of this point is guaranteed by the mirror symmetry. So we have the electric field lines are definitely pointing radially outward. Now its magnitude, what can it depend on? I mean, we will be using spherical coordinates, the easiest description of the system. Is everybody familiar with spherical coordinates? Okay, the spherical coordinates is, let's say, you have this coordinate axis. If you take any point, this is our origin, this is x, y, and z. You take the projection on the xy plane. This is what we call the phi. This is r, and this angle over here is theta. These are, if you tell me these three angles relative to x, y, z coordinates, these two angles and this distance, then I can determine the position of my system. So that's what we call the spherical coordinates. Now, let's go back and apply it over here. Let's say I want to find the electric field over there. We had already said that the electric field over here should be radially outward. It's in this direction. And let's say I consider another point over here. The electric field will also be pointing outward. And if these 2 points are at the same distance, what can I say about the magnitude of these 2 electric fields? They should be, if they are at the same distance from the center, the magnitudes of the electric field should be the same, because I can just rotate my system such that this point and this point overlaps. Now my system doesn't change on the rotations, so the magnitude shouldn't change. So they have the same magnitudes. But that already means that the magnitude, this number over here, can only depend on the radial distance and nothing else. It cannot, if this is my sphere, it doesn't depend on whether I am here or over there. The magnitude is independent of that. It's independent of the direction. It only depends on the distance from the origin. So what's the name of all the points that are at the same distance from a given point? Sphere. So if I consider a sphere, if I take as my Gauss surface, a sphere, that's a collection of points that are at the same distance from the center of my sphere, center of my charge distribution. On the sphere, all the points will have the same magnitude of electric field. So this is my sphere. I imagine as a Gauss surface a sphere of radius, let's say small r. This is my charge Q. Now, of course, this Gauss surface can be outside my sphere or inside my sphere. First, we will just study the case when my Gauss surface is out of my charged sphere. Now, what does Gauss law tells me? Q over epsilon 0. Now, E dot ds let's say we can just take any ds on the surface. ds is in this direction. But the electric field is also in the same direction at that point. Now E dot ds for that very small patch of surface is just E times ds. They're both in the same direction. So this is E times ds. So Q over epsilon 0 is equal to E times ds. But now I use one result that we had already seen. On this sphere, on this Gauss sphere, the magnitude of the electric field is the same everywhere. So on the sphere, on the Gauss sphere, E is just a constant. It is independent of which ds we are considering. Since it's a constant, I can just take it out of the integral. So this is the magnitude of this very small patches on the Gauss sphere. I'm just summing all of them up. That will give me the total area of my sphere. And hence we find the magnitude of the electric field as 1 over 4 pi epsilon 0 q over r squared. So it doesn't make any difference whether my charge is a point charge or it is uniformly distributed over a sphere. They create the same electric field as long as we are out of this charge distribution. Now, of course, we didn't yet write down the electric field. Electric field is 1 over 4 pi epsilon 0 q over r squared. It is in the radial direction. This is my electric field. Any questions up to this point? Now the next step will be to calculate the electric field inside the charge distribution. Yes. Well, you see, the applications of the Gauss law can work miracles. I mean, it might sound so confusing currently, but once you get used to it, I mean, if you want to calculate the electric field at this point using integration of, you just divide the sphere into point charges and integrate it, calculate the electric field of each one of those very small parts, and integrate over all the charges, it will take you pages. Gauss law, just in a couple of lines, you can obtain the same result. So it makes miracles. But it only works under very few cases, in very few symmetrical cases. Because only if we have a large symmetry, we can say that, okay, the electric field doesn't depend on these and these parameters. So for such a surface, it will be a constant on that surface, so we can just take it out of the integral. This is what we did. We first saw that the electric field on any sphere was a constant. So we just took the Gauss surface as a sphere, and we could evaluate this integral, although we don't know the electric field in terms of the unknown magnitude of the electric field on the sphere. It is just a constant. And so we know the area of the sphere, so which led us to the final result of the electric field as E as such a function. Your friend is asking, if I understood him correctly, is it possible to use this relation to calculate this area? But the problem is we can only apply this under very few symmetrical cases, and the areas of symmetric geometrical cases, they are all known. So there's no practical application. I mean, of course you can do that, but it will be like trying, I mean, as the saying goes, it will be like killing a fly using a cannon. Now let's look at what happens inside my sphere. This is my charge. This is my Gauss surface. Again, I will just denote it by the small r, the radius of my Gauss surface. And this is the radius of my charge distribution. Again, the electric field, because of basically the same reasons, will be radial. It will only depend on the radial distance from the center. E dot ds. This will again be just E ds. This will be E times 4 pi r squared. Nothing changes up to this point. So we just imagine the Gauss surface, which is again a sphere with origin at the center of my charge, center of the charge. We can just, E dot ds, the vectorial scalar product, just becomes the product of the magnitudes. And since the electric field on the surface is just a constant, I can take it out. What remains is the total surface. Now so this is one side of my Gauss law. What should I put on the other side? What is the total charge? I mean, not all the charge is inside my Gauss surface now. Just part of the charge distribution is inside my surface. Now the charge inside, the enclosed charge, is nothing but the volume charge density times 4 over 3 pi r cubed. So this should be equal to 4 over 3 pi r cubed rho over epsilon 0. This is what Gauss law tells me. Now, if inside the sphere was empty, then the Gauss law will already tell me that there is zero charge inside, so the electric field should have been zero. And hence the electric field, we can just cancel the 4 pi's, r squared cancels 2 of them. The electric field is 4 rho over 3 epsilon 0 times r. This is the magnitude of the electric field inside my sphere. Yes, the 4's are cancelled. And the electric field is 1 over 3 epsilon 0. Well, rho, we said that it was q over 4 pi over 3 large r cubed, r in the radial direction, 1 over 4 pi epsilon 0, q over r cubed, r in the radial direction. So the magnitude of the electric field, as long as we are inside this conductor, is increasing linearly. So if you would just plot the magnitude of the electric field as a function of the radius, let's say this is large r, it will increase linearly, and then it will start dropping. This is linear increase. This is, it drops like as 1 over r squared. Good point. It just looks like the gravitational force. I mean, if you remember what we had done in the mechanics, we said that if you have a hollow mass distribution, inside there is no gravitational force, outside it just behaves as if it's a point light. You see, the gravitational force and electrostatic force, they look quite similar. If you have gravitational force, it is given by some constant product of the masses in the radial direction. If you have electrostatic force, it is some constant times the product of the charges in the radial direction. Oh, now we are talking about the magnitude. They have similar forms. Their directions are the same. So whatever is valid in gravity, in some way, in some form, will also be valid in the electrostatic case. They have the same mathematical form. So anything we have derived using mathematics about gravity is also valid for electrostatics. The only difference between the two is gravity is always attractive, whereas in electrostatics we have attraction and the repulsion. That is the only difference between the two. So you can even write a Gauss law for gravity. And since you can write a Gauss law both for gravity and for electrostatics, they have the same 1/r² dependence. Other questions? No. We are not able to do that yet. You see, this law of gravity is Newtonian gravity. It's not general relativity. In general relativity, these are different. No, it doesn't have Gauss. It doesn't satisfy Gauss law. Okay, see you after the 10 minutes.